sequencing a little bit, essentially a nucleic acid passes through an artificial nanopore due to a voltage differential that's applied, and so we can measure the change in electrical current signal, which is characteristic of the sequence of the nucleic acid that's passing through the core at a given time. And so the standard process is to essentially sequence this raw electrical signal and pass it through a basecaller with the same means. The state-of-the-art basecaller is a neural network, a recurrent neural network, and this creates this outputs a basecalled sequencing read, which you can pass through your favorite long read aligner of choice to a collection of genomes or any reference. And so one question is if we're interested in off-target or on-target regions, for instance, genome A is off-target in this case, we would sequence all the reads and then we would line them, and then based off this alignment, we would throw out reads for downstream analysis. But this is pretty wasteful because we are still sequencing all the reads, and so we're still spending a lot of time doing sequencing reads that are irrelevant to our process or our analysis. So there's something called adaptive sampling where we can essentially inject the read from this nanopore in real time by reversing the voltage across the pore. And so Readfish is the tool to do this, which uses Minimap and essentially base calls each read as it's being sequenced in read prefixes, aligns it using Minimap, and then makes a decision according to the mapping to eject by sending a signal to the nanopore API and choose the nucleic acid out of the pore, or if it's on target, you can send a signal to continue sequencing to completion. UNCALLED is a tool that identifies likely camera sequences directly from this electrical signal, and it bypasses this base calling step, which is a computational bottleneck process. And it essentially does approximate mapping to these genomes and does the same eject or continue sequencing decision. And so crucially, it uses an FM index as underlying data structure. And so Sigmap uses a KD tree for the same purpose, and it does the same has the same sort of goal as UNCALLED for signal-based mapping. So you might have noticed that the KD tree and the FM index are both don't scale very well with large repetitive genomes or references, in particular a collection of genomes like a pangenome. And so one question and our main goal is to see if we can apply some sort of sublinear index that scales better for large collections of genomes. So one example of this is the R index, which, like I mentioned before, unlike previous methods, can handle these large collections of genomes like a pangenome or repetitive genomes that you find in eukaryotic genome. And so SPUMONI, which was developed by our group by Omar Ahmed over here, uses the R index to classify reads using matching statistics, which are and so the R index is essentially a length encoded Burroughs-Wheeler transform, along with a couple of auxiliary data structures which enable the computation of matching statistics in big O R space, which is where R being the number of runs in the Burroughs-Wheeler transform. And crucially, it also allows you to compute the matching statistics in a length that's linear with respect to the query length. And so just to define matching statistics here going forward, they're essentially what we call half maximal exact matches, so the longest right extendable match any position in the query. And so here we introduce Sigmoni, which is essentially a signal-based reclassification system using the R index. And so the idea is to quantize your signal, this continuous electrical signal that you get from the sequencer, quantize that signal into some alphabet space that we can define, and then we project the reference into the same alphabet space, and we can compute exact matching, exactly how we would with basecalled reads. And so this is very similar to SPUMONI, but crucially we avoid this computational bottleneck of basecalling, and we show that using a rapid signal binning procedure, we can get very similar accuracy without the basecalling. And so just to get into the methods a little bit, here is an electrical current signal example, and we kind of draw these arbitrary bin boundaries, which is what we call them, where we're partitioning the picoamp space of the current, and we can assign a bin IT to each stretch of signal in the current. And to treat the reference the same way, we digest the reference into k-mers, in this case 6-mers, which represents the length of a sequence that is characteristic of the output electrical signal in the pore at any given moment, and we can compute find the expected current for each k-mer and then apply the same binning procedure to that to the reference. And so we can pass this reference and this queries, now that they're in the same alphabet space that's discrete, into the R index and use these sequence-based indexing procedures for computing exact matches. So crucially, as an aside, we can also get around segmentation errors that come with dealing with a continuous electrical signal by merging together runs of homologous bins using some sort of homopolymer compression scheme. And so, like I mentioned before, these bins are arbitrary, so we can give them just any sort of label and go ahead with our text indexing as we always would, and pass the index or the query of the reference into the R index. And so, just as an aside, what the R index looks like, on the left you see the Burroughs-Wheeler matrix along with the BWT and a suffix array, and SPUMONI also introduces the concept of a document array where we assign each suffix in the BWM or each suffix in the suffix array an ID, which is labeling it with the reference in a collection of references that makes up the reference, and so we can figure out which reference in this pangenome or collection of references the suffix comes from. With the R index, crucially, we can subsample this at the run boundaries as opposed to in equal intervals for the suffix array as you would in an FM index. You might notice by subsampling at unequal intervals, it becomes harder to do things like locate queries like you would with an FM index, but we introduce a novel approach to this by essentially what we call shredded documents, where we cut up the documents into equal-sized partitions and we use those as our document IDs as opposed to the entire reference. And so this allows us to find or assign suffixes in our suffix array with approximate regions in the references that make up our pangenome reference. And so the output of the R index is the set of the sequence of half mems across the query in every position, the longest extendable right exact match. And so we can project this string of or this sequence of exact matches back onto the reference using this approximate mapping technique that I just mentioned. And as you can see here, what we call a Manhattan plot is a concatenation of a couple of bacterial genomes and the yeast genome, which make up a mock community in this experiment. And we take a set of mems in this single read, and we can get the approximate mapping information, plot them together, and you can see the mems cluster very nicely at the true origin of the read, in this case in Listeria, and so we can use this to make our classification decisions downstream. And so to get to some speed results first, Sigmoni is significantly faster than other signal-based tools, so I'm going to compare it to UNCALLED and Sigmap in particular. In particular, for single chunks, which is the smallest discrete length of time that you get from a sequencer is around 450 base pairs. We're around an order of magnitude faster than the previous tools. And when working with full read signal, we are also significantly faster than both tools in a mock community sense or experiment. And crucially, this is very important for adaptive sampling because every second matters. The faster you can make that accurate classification, the less irrelevant sequencing we need to do, and the more time and cost savings in the sequencing pipeline you'll get. And so, like I mentioned before, the R index enables very space-efficient index construction in this big O core space, and scales with respect to the uniqueness of new sequences you add to your collection of genomes, as opposed to just linearly with the length of the reference. And so you can see that in this example where we can index over 7,000 bacterial genomes in under 3 gigabytes. And we can also look at a collection of human genomes, in this case 6 human genomes, where Sigmoni significantly outperforms other signal-based methods in their index construction. And we can also look at the scaling here, where if we do 5 extra human genomes to create a small pangenome, the scaling is very efficient, unlike other tools. And so, in accuracy results, Sigmoni outperforms UNCALLED and Sigmap in both long-read binary classification and a mock community. And we can also extend this to multi-class classification, where we can not only decide if it's bacteria or yeast in a mock community, but also which bacterial species it is, and get approximate mapping information. As you can see here, the recall is pretty high for all 3 tools. When we start looking at the precision, it might not be very clear here, but UNCALLED and Sigmap tend to have a pretty poor precision, unlike Sigmoni, which can very accurately classify reads. And so Sigmap and UNCALLED also fail to classify a lot of reads because of signal noise, and Sigmoni can classify those reads In an adaptive sampling context, Sigmoni outperforms uncalled in binary classification and performs comparably with Sigmap, and along with the significantly faster classification, we enable pretty high cost and time savings in nanopore Sigmoni. And lastly, we can identify on a chromosome level, do multi-classification in human reads, and this is the only signal-based method that can perform human genome scale multi-classification. And so some conclusions, signal-based classification is very difficult due to the noise in nanopore signal, but Sigmoni is able to apply this signal binning procedure and use exact matching to overcome this. And so we can also represent a way to get approximate location information using the R-index, which we've shown to map sequencing nanopore read signal. And we also show that compressed indexing is very useful in metagenomics and pangenomics applications for rapid read classification, which can improve potentially reference bias and downstream filtering tasks. So I just want to thank my group and collaborators. If you have any questions, please see my poster in 20 minutes.